So good afternoon. I hope the connection from rural England will keep up. I have an animation going on the screen, which you may or may not be able to see at this speed. I'm Pierluigi Vidali. I'm presenting some of the synthesis results from Primavera after nearly 4 years of the project. And I want to give you some motivation and maybe a couple of highlights that stem from those motivations. As a start, I have an image here of 3 different simulations that we performed as part of the frontiers of climate modeling in Primavera. These are global climate models that we have developed within Primavera to run at 5 kilometers. And we're actually participating in an international comparison called Diamond, which was run about halfway through Primavera. We're still very busy analyzing the results of these simulations. These are quite advanced GCMs, and we're part of what we wanted to develop within the Primavera project. These are 3 ensemble members. We just spawned a little bit of chaos in simulations as we started them, and we have here 3 ensemble members. You can see that after a few days already, the solutions, the way the hurricanes are forming here in the Atlantic is quite different. And so we have 3. There is one spawning up here quite nicely. So these models are able to simulate hurricanes. And this starts to tell us about uncertainty and uncertainty connected to model formulation. So just to start with motivation, every year we hear from, for instance, in this case, the insurance sector, that losses due to natural hazards are increasing. They're also quite variable from one year to the next. This is what is shown up here in the top panel that I have here. This is compiled by Munich Re. We're talking about hundreds of billions of losses each year, and the events are colored differently depending on what sector they come from. The hydrometeorology or hydromet are the blue and green, the vast majority. And the question to us is, are they on the rise, and also why are they different each year? So predictability here is an issue. But you can also see on the map, this is the map for 2017 and this is the map for 2011, 2 very important years, very big losses. The losses are incurred worldwide, they're not localized. So this is one of the important reasons for having a global project that uses high resolution. So as we resolve these hazards with higher and higher resolution, we're also concerned with things that are near home, so things that directly affect us, and also things that are not near home and might affect us through, for instance, in this case, the insurance sector. Several countries in Europe are exposed through the insurance sector, but also through the market chains, which are very complex. There are events happening on the other side of the planet that through the market chains can very much affect our society here in Europe. And also many of us lead very international lives, so we're increasingly interconnected. The other aspect is that if you look at now what the amount of losses is, so these are the loss-making events, and this is the amount of losses, you can see that the time series is not so terribly correlated with the number of events. And this is because the events incur losses depending on the location, and sometimes these locations are very small locations, or there is a very particular exposure at the location. So all the detail of the exposure as well as the detail of the hazard is important, thus again, high resolution. Just to bear in mind, if we're talking about a single hurricane nowadays, we're talking about 25 billion incurred losses, and this is important for the talk we'll hear next from Louis. So Primavera questions. So there are many interesting and important scientific questions in the World Climate Research Program, and they are listed as grand challenges. One of them is, what are the relative roles of large-scale, regional, and local-scale processes, as well as their interactions for the formation of extremes? So I was talking about hurricanes, that's one type of weather and climate extremes. This is the motivation for dealing with such things with global models at high resolution versus using a number of regional models, because these things are interconnected. Again, the processes that regulate what happens to hurricanes in the Atlantic often are spawned in the Pacific Ocean, and many of the characteristics of the Atlantic storms that come to Europe are decided on the west side of the Atlantic. So a lot of things happen remotely that end up impacting us locally. So these are the types of problems. There's a whole list here, problems that we are dealing with in Primavera with GCMs down to about 25, maybe 20 kilometers. And then as we look into what clouds do in the climate system and how the system may respond to global warming through the interaction of cloud radiation, This is where we're going next with these frontier simulations and new models that we're building. We're pushing those global models to about 1 kilometer. I showed an example of global models at 5 kilometers, but this is where we're going next, and this was part of the delivery of Primavera to the community of new advanced models that we will be exploiting in the next 20, maybe 10, 20 years. So Primavera is a project that is mostly concerned with the global climate system and with building and operating global climate models. It's been funded by European Commission for the last 4 years. There are 19 partner institutions that are developing and running 6 European GCMs. These GCMs have resolutions that are sufficient to represent processes that previously were in the realm of regional climate models. But what we are interested in is the two-way interaction between these things. It's not just about the downscaling, understanding the local risks, but the interactions between storms and large-scale environment and global circulation. So when we talk about high resolution, one of the important aspects is that we do deploy high resolution in the atmosphere, in the land surface, and also in the ocean. So just for you to have an idea what a local landscape looks like, this is a depiction of the Alps in a typical climate model that is used for global assessments, for instance, the IPCC, in Intergovernmental Panel on Climate Change Assessment. You can see the Alps are very low in height and very smooth in the typical GCM. And as we move to 25 kilometers, the Alps start to be much better represented. You can see the major lakes, and you can see the valleys in which rivers are falling. So if we're talking about water resources, separating the north side of the Alps from the Italian side of the Alps, separating the rivers that are filled by precipitation excess to the north from what happens to the south is important. But also the interaction of the airflow, so the interaction of cyclones coming from the Mediterranean with the mountains, generating extremes of precipitation, but also the snowpack, which is very important for water resources, is also of crucial importance. So the realism of these models is connected to resolution. And this is another panel showing you where we're going next with the 5 kilometer GCMs, much higher mountains, much higher snowpacks, much more violent interaction between cyclones and the elevated terrain. Very strong runoff and possibly very large peaks in the rivers that we simulate in such models. Now, looking again at the global picture, so we've computed over the last many years statistics of how we simulate, in this case, precipitation. This is a composite of all the models we run in Primavera. We're looking at the amount of precipitation throughout the globe. Wherever the colors are in red, it means that the high resolution models simulate less precipitation than the low resolution, the classic GCMs. And wherever it's blue, they simulate more precipitation. And one very notable example here is around the maritime continent. We have a lot less precipitation on the ocean between the islands and more precipitation on the islands. It is also true that we generate more precipitation, perhaps it's difficult for you to see around major mountain chains, but also where major ocean currents are, for instance, here in the Atlantic and also around the Kuroshio current in Japan. On the right-hand side are the couple models, the models in which we run both high resolution atmosphere and high resolution ocean. And you can see there is a very, very big change in the amount of precipitation in the tropical area. And if we look at arrows down here on the bottom are maps of where we compare precipitation to observations. In these coupled exercises, there is a massive reduction of an error that has been long-standing for the past 20 years in all of these IPCC assessments. So this is a major breakthrough in terms of running coupled GCMs, but also you can see the little dots that surround this brown area. It tells us that all the models agree. So there are places, do not get me wrong, where perhaps the error is increased and also the models agree. And perhaps if we look further and we challenge observations, we might discover that in such places, indeed, the models are wrong, but we also might discover that the models are suggesting that we should go and observe in a much more careful way, because they're now simulating very intense systems that very much challenge remote sensing and the classics of the observational system we have in place nowadays. So these results are not just important for progressing our ability to simulate the climate system, but also for interaction with the observational community. Another aspect of the global climate system, this is an index that has been calculated over all of the oceans. I'm showing you a snapshot of the Atlantic Ocean for 3 different Primavera models at low resolution, mid resolution, high resolution, and ultra high resolution. And where it is red, this shows that the atmosphere and the ocean are more coupled than they would be at low resolution. And this means that the state of the ocean is much better able to influence the state of the atmosphere, maybe actually adding predictability. And if you've seen what I was pointing to in the previous maps, where the precipitation is increasing, this is exactly happening over these regions of stronger coupling. This has to do with the Gulf Stream, and it has to do with evaporative processes influencing the growth of cyclones, and these are storms that eventually will come to the shores of Europe. So this is very important for the predictability of the storms that impact Europe in terms of their nature, how much precipitation they will cause, but also how many and where they will travel and eventually make landfall. Another motivation for Primavera was understanding the changing nature of the storms that are coming to Europe. There have been many suggestions in past simulations, which actually were realized several times in the last few decades, and a recent example is Ophelia, of tropical storms actually migrating all the way to mid-latitudes and eventually possibly making landfall in Europe. And we've had a few very close calls recently. And doing a morphological analysis of such storms, it shows us that they have a mixed nature. Some of them arrive to Europe with a full warm core cyclone nature, like a hurricane, and some of them arrive in hybrid form, so with part of the characteristics of tropical storms and part of the characteristics of extratropical storms that are driven by baroclinicity. The type of hazard they pose is quite different depending on their nature. The type of winds they have at landfall and the type of precipitation they have at landfall can be much higher in intensity than the classic extratropical storm. Simulations in Primavera, which were pioneered by the KNMI group a while ago, indicate that with climate change, we might see a substantial increase in the number of such storms coming to our shore. So understanding where we are with the current simulation and then looking at all the simulations that involve climate change and understanding the increased risk that might be posed by storms we're not being so used to seeing in Europe is very important. And in fact, we had a comparison of Primavera models to reanalysis. We found in reanalysis that currently about 3 to 5 storms each year have a tropical origin, have this different nature, so pose a different risk to Europe. And what we could see that both the atmosphere-only GCMs and the coupled GCMs at low resolution underestimate this risk. Basically, these storms are not represented, while the high resolution GCMs that we were able to run in Primavera have virtually zero error in simulation of something that is actually quite rare and quite difficult to simulate. And in fact, if we look at how many cyclones, as we increase the resolution, we do increase this to that number I told you about, 3 to 5 each year. And in terms of the error, we see that the models also agree with each other in this. It's not just a matter of the models predicting this, but they all agree about the location, the number, and the interannual frequency of such events. And this is really important for what threatens our shores in the future. So we need to start to prepare for the arrival of storms that we're not terribly used to seeing. We might have more and more in the future, but this is a pre-existing condition for trusting the models. And again, the GCM agreement is very important. And again, it is the GCM agreement happens over those regions that I previously showed you have a stronger coupling between the ocean and the atmosphere. Finally, in terms of the models that we have delivered to the rest of the community in preparation for the next round of ITCC reports, so this will be the next generation of models. As I said before, we ran a number of GCMs, and one of them was the Unified Model of the United Kingdom, which were taken down to between 3 and 5 kilometers globally. And this was motivated by the idea of Matsuno. He thinks that we should develop a tropical analog to the mid-latitude numerical experiments of Phillips, 1956, and Smagorinsky, 1963, which were the foundations of modern weather prediction. The modern weather models that we run were coming out of those experiments in the 50s and 60s, but we're never able to actually simulate tropical weather systems. And we are starting to now develop GCMs that do have a glimpse of that capability, and further, if we go to 1 kilometer, might have quite a credible capability. And as I was saying before, we might increasingly be affected by storms that do have a tropical nature. And one of these, so this is an image in the paper that we wrote together. One of these is a satellite image, and all the others are models. And the idea of Tim Palmer is that these models might become so realistic that it will be hard put to discover which one is the satellite image and which one is the model. So there's a sort of Turing test for weather and climate. And in this exercise, we started to extract a number of storms, and this is an example of having extracted hurricanes. This is the so-called wind pressure relationship. In black are observations, and in orange are the hurricane intensity. So two metrics of intensity of hurricanes are simulated by these models. And you can see that some of the models in the ensemble are starting to do a very credible job, and possibly these are the highest, the ones that are coming closest to that 2-3 kilometer resolution, while models like ours that are still sitting at 5-kilometer resolution globally do simulate the vast majority of the storms, but at the extremes are still underestimating the intensity. But what is interesting about this is that unlike the classic studies that use limited area models, so just over a region, we are studying such phenomena under full global conservation. So energy and water are conserved, and we can then try to understand what happens when we have a closed system in which there is only a limited amount of energy and water that we can process through such storms, and then understand what it is that is in store for the future. Will we have more? Will we have less? Will we have more intense? With such models, we can start to more credibly make such predictions because we have a better understanding. And again, we're dealing with full conservation in our system. And I'll summarize. So the first results show that some historic biases that have been in our community for about 20 years have finally been reduced, both in the sea and the atmosphere and also on land. I didn't have time to show that. What is very important here is that our models agree. There's a very strong amount of agreement on the regions, and the amount of precipitation that shifts around in some regions much more intense. And this agreement is over a very large portion of the globe. There is also evidence of stronger coupling between climate system components, which were all run at high resolution, low resolution, and cross-coupled resolution. And this agreement and this coupling go together, and the coupling happens over very narrow regions across the globe, particularly where important currents are. We have produced very large Primavera global data sets, which can be exploited to produce event sets, so storm catalogs, for instance. So we have about 5,000 years of 20-kilometer simulations available globally. That is about 500,000 tropical cyclones that are able to be studied. They can be downloaded and studied by external users, by industry, whoever wants to do that. We also need to be, perhaps as we interact with industry, we need to be as open as we are, publish our data, make all the tools available and all the data available, and maybe then we can work together to build models that allow us to predict from the hazards that we produce and quantify what the risks are. I want to stress the resolution is no panacea, but we do see some strong benefits in the understanding of certain chains of processes in the climate system, and these outweigh the cost. These are very costly experiments and the shortcomings, because again, they also have their own errors, and sometimes the errors do increase, they're not just all reduced. For the future, we will continue to exploit our data sets, which will be around for many, many years, and we will continue to insist on the process understanding, not just on using the data raw as they are, but following these process chains and following the understanding. And this requires a community approach. All the data are published for the entire global weather and climate community to analyze, but also for external users, and I invite you to work with us to further understand the value of such data sets. And I'll stop here.
Thank you very much, Pierluigi. I would like to remind everyone that you can ask the questions. There is a question field that you should be able to access, and you can ask the questions straight away there before you forget them, and then we'll go back to the speakers at the end during the discussion part. And now we have our next speaker. It's Philip Stanzel. Philip is a hydrologist in the Water Resources and Hydropower Department of the Global Engineering Consultancy AFRI in their office in Vienna. Philip is the Primavera user who has been collaborating with us, I think, the longest in the project. So I'm very curious to see what Philip learned from applying Primavera data. And I will now share the screen with him. Excellent. We can see it. Philip, we don't hear you. Yes, now we should be able to hear you, Philip.
Hello, I think now you can hear me. I had the same issue as Pierluigi before. I couldn't unmute myself, but now I'm hearable to everybody, I think. Good afternoon. I will present, thanks for the introduction, Dragana. I will present one of the use cases of the Primavera project. That is, the use cases are something like a co-production exercise where impact researchers or users of the climate model data use the data already during the phase of the production in the Primavera model. And our use case deals with the climate impact on hydrology and hydropower production on the upper Danube River. And when I say upper Danube River, I mean the Danube up to Vienna. So, and that's the reason why you can see Vienna on this picture on my first slide. And I am at the moment also located here. Switch to the next slide. The background, how it came to setting up this use case was that at my company, A3, was previously called PRI. That's why I say PRI and A3 here, because on some slides there might still be some reference to PRI. We have investigated the impact on climate change on the upper Danube, which is the Danube in Germany and Austria, already in some previous projects. And we have there we have applied different generations of regional climate models. And that's why we were interested, and we also thought that maybe our clients that were previously interested in updating climate model generations for future scenarios of Danube River discharge might be interested in that. And another reason why we were interested in collaborating for the use of high resolution global climate models is that we are a global company applying our services in different parts of the world, and so far it is very difficult to obtain data sets for all different regions of the world. So we were interested in having a global data access to a global data set that we could maybe use in different parts of the world for assignments in Asia or Africa, where we are also active. And that's how this collaboration between A3 and the University of Reading started. And here, that's the objectives that we formulated in the beginning. One was to evaluate the skill of the historical runs of the Primavera GCMs from a hydrological impact modeling perspective. The second major objective was, of course, to simulate future discharge scenarios for the Danube. So that was maybe the impact, our impact researchers' focus, and the evaluation of the skill was more the focus of the climatologists of University of Reading. And of course, we were interested in comparing the results with Primavera models with previous results that we achieved with using RCM data of different generations, and also to compare the results between different Primavera models, different resolutions, coupled and forest runs, as we have seen before. And finally, to explore the impact on hydropower on the Danube. And as a use case, we were also aiming to contribute to the evaluation of this co-production framework that was applied in the Primavera project. Okay, so now some details. That's the study area. That's the Danube. You can see up here, you can see the full Danube basin, covering large parts of Eastern Europe. But our focus is on the upper Danube basin, which is up to Vienna, this in the center of Europe. It is largely influenced by alpine topography, as we have seen before. That is much better resolved in high resolution models. That was the reason why we have previously only used regional climate models, because they could resolve the topography of the Alps adequately. And then it has also a larger lowland component here. And in the main Danube River, it is an important waterway, so navigation plays an important role here. So we're looking at the impact on if we look at the impact on discharge, on the discharge regime in the Danube, we look immediately we look onto the impact of navigation, for ecology, because there's important floodplains, and what is also the focus of our use case, we look onto hydropower generation. Hydropower is an important source, most important source of energy in Austria, and most of it is produced along the Danube River. And then that is we have a hydrological model, of course, for this basin, which has been tested and calibrated well in the previous projects, and we have exceptionally long data series here of simulations that can be compared to observations. You can see here a run of simulation from 1887 to 2007, and you can see both observation and simulation just matches very well. And we use this hydrological model with input from the PRIMAVERA climate model data. You can see on the next slide, we applied, as Pierluigi has already explained, it's a long-lasting project, also due to the long time frame of generating these high-resolution models. So we did our first analysis in 2018, where we just looked at the historical runs, and then we did now very recent analysis with scenario runs, but with different model sets, which is somehow, as we saw, one of the difficulties in the co-production that we had to adapt to different available data sets, or what we thought that would be available at different moments in time. So what we did first, and these are very rough pictures, not formatted well, but it's just to give you an overview of what we have done. We looked into the evaluation of the historical skill of the climate model data to represent historical climate over the Alps, so over the Alpine river basin. And the red colors are always the results with the Cortex models, and the blue ones are the ones with the URPA. The blue ones are the ones with PRIMAVERA, and we applied an aggregate measure of skill for both looking into mean and variability of precipitation and temperature, and we did that for the entire basin, for the whole of the basin, and we did it for the hydrological model unit, so that's much smaller units. And we saw that on one hand, we saw on the left picture, you can see that where the comparison of the mean basin and of the hydrological model units, you can see that the results are quite different. The PRIMAVERA models in the beginning looked seemed to represent the climatology over the Alpine basin better than the Cortex models if you looked at the mean basin values, but the picture is different if you look at the hydrological model unit. And we have not repeated the full analysis now with all the PRIMAVERA models that we analyzed in 2020, but I can show you the results for the hydrological model units, where you can see that, and here the models are ranked, so you can see I'm not going into detail on what the numbers mean, but the models are ranked, so the better models are here. So the PRIMAVERA models are not as skillful as the Cortex models, but they are also not much worse. And the one with the patterns here are the ones that are forest models, and I think it's good that they are. I think they should perform better for the past. But yeah, you can see that we were actually surprised that they were not that they were performing rather well here, because it is difficult to match the hydrological model units well, because they are sometimes very small and range up to high mountain areas. And so then I show you some results for the discharge simulation. So that's already results from the hydrological model. It's future discharge scenarios as compared to the reference scenario. Here in the center, you can see the mean seasonality of discharge. So that's January through summertime back to winter. You can see that in January, in springtime, there's snow melt. Discharge into Danube increases, and then in summertime, when there's less precipitation and there are higher temperatures, discharge decreases again to low flow in late fall and winter time. So that's the black reference line, and Then you can see these colored future projections for the period of 2020 to 2050. And here on the upper part, you can see the Primavera results, and in the lower part, you can see the previous Cortex results. You can see that the general shift is very similar, and it's the typical climate change shift for snow-dominated regions. You can see earlier there is more discharge in winter due to higher temperatures. Then there's earlier snow melt here, and then there's a kind of decrease in summer due to the higher temperatures and stronger evaporation. That's similar in both results, but what we saw with the Primavera models now is that the decrease in summer and early fall is much stronger than in the Cortex models. And we also, at the same time, we saw a smaller increase in discharge in winter. And that leads to a specific situation here in the beginning of winter or during fall, where the projections of the Primavera models were much lower than the Cortex projections. And if you translate that into a duration curve, it's a hydrological analysis that shows a distribution curve of the discharge in a river. And here you can just see the lowest 20% of the discharge on the right side, which is the low flow period are the low flow events along a river. So just the lowest 20% of discharge. You can see that the previous Cortex results showed an increase in the low flow discharge from the black line in the reference period to the red line in the future scenarios, because of the increase in winter discharge mainly. But the Primavera results show a decrease here, and that's actually a quite strong difference here. And that's due to the stronger decrease in summer that leads to lower fall discharge that doesn't go up that much in winter time. And that's actually very relevant for navigation and also for hydropower production in winter time. And just a short look on what was the driving force behind it. When we compared Primavera data with Cortex data, we saw that summer temperature the projections for summer temperature were much higher in Primavera. So there is a much stronger warming projected between 2 and 4 degrees. And in Cortex, we never reached more than 3 degrees. So that's one of the reasons why the drying up of the summer discharge is much stronger, because of the higher temperatures. And when we looked into the fall precipitation, we also saw the fall precipitation in Primavera the Primavera projections were lower than the Cortex projections. So then that's another reason why discharge in fall was lower, because of the lower precipitation. So that's just very first analysis, because we just looked into this scenario data in the last months. And I will conclude with an outlook on what we think that we should still look at. Of course, into more detail in this analysis between previous RCM results and new Primavera results. But it's also, of course, interesting or important to look into the differences within Primavera model data between coupled and forest models, between high resolution models and low resolution models. And probably the most important part is to identify the physical representation of large scale processes behind these differences, to understand if the different processes that are projected for the future are more reliable or are more credible than previously. So can we maybe rely better on these new GCM, high resolution GCM results than we can rely on the previous RCM results? And in our specific use case, it would be also important to explore then the impact on hydropower along the Danube River. And yeah, just one very short wrap up. First conclusions with the use of Primavera scenarios showed a stronger reduction in Danube low flow, with important implications on navigation and hydropower production. And when we looked at the skill of the representation of the historical climate in the Primavera data over the Alpine Basin, we saw that this is very much scale dependent, but and Primavera data were not much worse than previously analyzed RCMs. And in our outlook, we will focus on analyzing process representation in the different GCMs, and our outlook from the side of the user, company AFRI, we will, or we hope that we can use these high resolution GCM data that we have now been able to explore in this use case in further impact studies globally. Okay, thank you very much.
Thank you, Philip. Very interesting. We will continue now with the next speaker. With us is now Louis-Philippe Caron, a colleague from Barcelona Supercomputing Center, Earth Sciences Department. Louis-Philippe is a climate scientist in the climate prediction group. Okay, you have the sound now.
Okay, great. Can you hear me, Diana? I assume yes. Okay.
Yes, please go ahead.
Okay, thanks. Yeah, so I'll just be presenting a brief overview of the results of some of the studies that were done on tropical cyclones in Primavera. As Pierluigi mentioned earlier, tropical cyclones are an important part of Primavera, and in part because of their impact, also because we expect that it is one of the phenomena that will be improved with resolution. Before I do, however, let me just acknowledge the work the people who have actually done a lot of the work that I'll be presenting here. So Malcolm, Pierluigi, and many others. Okay, so just for those who don't know, a quick recap on what the protocol for the Primavera simulations were. So for the climate model, because it's at higher resolution, it's a lot more computationally expensive, and the standard DEC simulation from the CMIP6 protocol were not realistic. So we had to come up with a new protocol called the IRIS-MIP, and this consists in 50-year spin-ups, and then 100-year of control simulation with constant forcing. And then starting in also 1950, then the parallel simulation where we actually use observed forcing until 2014, and then future scenario until 2050. And this is done both in couple mode and in atmospheric only mode. Okay, so I will just present some highlights, like I said, and yeah, if you guys want to know more, we can discuss it later. So the first, so the first result is from a paper by Malcolm that was published last year, and it's on the impact of resolution on track density. So the first row shows the improvement in track density, and we showed that it's an increase, a general increase in track density in most basins. Maybe the Atlantic not as much, but in most basins we see an increase. The second row is the error. So we generally see a reduction in error in most basins. I'll just point out the East Pacific, where we expect there to be one of the larger improvement because of the importance of mountainous region in the formation of the tropical cyclone in that region. Then moving on to, just focusing on cyclones in the Atlantic that actually go through extratropical transition. Like Pierluigi mentioned in the top row, this is the bias at low resolution and for the ensemble, and the second row is the bias at higher resolution. And you see that the bias in the number of storms that undergo extratropical transition is actually removed, which is quite astonishing, actually. That being said, so going back to track density, there's a wide divergence of response across models. So just focusing on the second and fourth column, this is the difference between higher resolution and lower resolution models. We see that, yeah, for some models we see a large improvement, but for some models actually we see no change. And actually for some models, like the French model CNRM at the bottom, the second row, actually see a decrease for some regions. So generally there's an improvement in the track density, number of cyclones in the distribution, but yeah, it's not the same response to all models, and yeah, it's not even for some models there's no change. So that probably suggests that the parameterization has an important role to play. Yeah, so this has an impact also on the residence time. So this is a distribution of tropical cyclone across latitudes for the CMCC model. So the full line is the dark line is the very high. The dark full line is the very high resolution in APMIP mode, and the dashed dark line is the very high resolution in couple mode. You can compare that with the full dotted line. The lighter red, you can see that there's an improvement in the residence time as we would expect from the previous result. Now looking at the impact of resolution on tropical cyclone-induced precipitation. So looking at the first column, we see that for most models, we see an increase in tropical cyclone-related precipitation. So each row, I should say, is a different model, and then the first column is a difference in precipitation between the high resolution and the low resolution. So yeah, we can see this case a bit confusing because we would expect blue to be more precipitation, but in this case, red is more precipitation, and yeah, we see a general improvement, a general increase in precipitation related to tropical cyclones. Then you can break this increase into the part in the second column due to the change in precipitation per cyclone, which is the second column, and then in the third column, the change due to the increase in the change in the number of tropical cyclones. And you can see that this signal is basically controlled by the change in the number of tropical cyclones between the higher and the lower resolution. And we do notice a decrease in number of the amount of precipitation per cyclone between high resolution and low resolution, the second column here. This is due to the fact that the high resolution has a lot more weaker system. Yeah, an interesting study that was done by Enrico Scocimaro at CMCC using this PRIMAVERA simulation. So he showed that, so what you see here is the amount, composite of precipitation between, well, it's a difference, composite difference in precipitation between the very active and less active typhoon season. So the red shows, yeah, an increase in precipitation over the Western North Pacific when you have a very active typhoon season, which is not entirely unexpected. But what's interesting is this actually comes with a drying over the maritime continent. So the blue box there. So the left one is composite used all years going back to 1979. But then you can see, yeah, but maybe this is ENSO. So then you repeated the exercise using only ENSO neutral years, and this is the second figure on the right, and the signal remains the same. So this is derived from observation. Then look into the PRIMAVERA simulation, and then on the left is what happens if you use the low resolution version of the CMCC model, and then on the right is what happens if you use the same analysis using the high resolution model at CMCC. And you can see that at low resolution you have no signal at all, but if you increase your resolution, and I think the resolution is 50 kilometers, yeah, then you recover the observed signal. Another result that was interesting that was in a paper by Benoît Ragnard is that, okay, so the top row is the amount of precipitation, composite of the 200 tropical cyclones, the composite in precipitation of 200 cyclones. The second row is a similar composite of 200 storm in the low resolution model. The third row is high resolution. And then the bottom row is the difference between high resolution and low resolution. So what we see is that for many models, actually, we do have an increase in the center of the storm in terms of precipitation, so like a more intense storm towards the center, but this is compensated by a decrease actually around the center. And if you do you integrate the total change in precipitation, so for some models, it's actually very low. So contrary to the number of storms, for example, the resolution doesn't play a very significant role in the total amount of precipitation per cyclone over a large domain. However, if you zoom in towards the center of the storm, of course, then you'll have big differences. And this he linked this to the fact that actually the amount of precipitation is controlled by the amount of convergence at the large scale, so up to about 500 kilometers away from the center of the storm. Something else that you would expect, of course, is that with the increase in intensity, we see stronger storms. So on the left here, you see the usual distribution PDF of intensity, categorized according to the Saffir-Simpson scale, and the full lines are the high resolution version of the model, and dash line are the lower resolution. You can see that when you increase the resolution, then you start reaching higher intensity. So intensity here being measured by the maximum surface wind near the center of the storm. And on the right here is the pressure wind relationship that Pierre Luigi mentioned earlier. You can see that for some model, well, for all models, the relationship is improved with resolution, and for some model, we actually, the French model, we match observation quite well. Although then you can, whether or not we would expect a 50-kilometer resolution model to match observation so well is another question, however. But yeah, maximum surface wind increased definitely with resolution, but that's not a new result. What's interesting, something that we've looked at here at the BSc, is the impact of resolution on the integrated kinetic energy. So usually when storms are measured, often they just look at the maximum surface wind near the center. But what we decided to do here is take into account all the wind field where the winds were above a certain threshold. So in this case, if the winds were above tropical, well, to qualify as a tropical cyclone, which is 17 meters per second. You can see on the two figures on the left, the areas that would be considered for these two examples. And then you can plot the scatter plot here on the right, and you can plot the area on the y-axis, and the x-axis is the intensity, and then the color gives you the integrated kinetic energy. And then we compare here two models, one low resolution, one high resolution. The circle are the low resolution French model, and the triangle are the high resolution French model. And what you can see is that actually the integrated kinetic energy are fairly similar between the two resolutions. So the colors and the dotted line also, the dash line, sorry, gives you interval of integrated kinetic energy to go along with the color bar. So you can see actually that the two versions of the model give similar integrated energy, but for a very different reason. So for the lower resolution, which are the circle, you actually have much larger storms, and then for but weaker, and then the higher resolution, yeah, smaller but more intense. But they seem to, the change in size seems to be compensated by a change in intensity fairly well. And then we try to correlate this with correlate the integrated kinetic energy with the maximum surface wind speed, the total Ike area, and the minimum sea level pressure, which is the table you see at the bottom. And of course, the Ike is controlled mainly by the size. But what was very interesting is that actually in low resolution, you get a better correlation with the maximum surface wind speed than with the minimum sea level pressure. If you go at high resolution, this is reversed. The changes aren't very big, but they are consistent across basins, actually. So not too clear why this happened yet, but we will be looking into this a bit more. And that's, yeah, something else that was looked at is the impact of stochastic physics on tropical cyclone track density. So this study was done with Pierluigi. So stochastic physics is introduced in the model to try to sample the uncertainty due to parameterization. And yeah, on each column is a different resolution of a model. And on the first column is the base case, and the center is the same model with stochastic physics turned on, and the last column is the difference between the two. You can see that in general, introducing stochastic physics increases the amount of tropical cyclones in the model, and quite significantly, for some cases up to 30%. And in this study, Pierluigi tried to break it down between, well, where this change originated from, and tried to break it down. Is it just more tropical cyclones forming, or is just more seeds that occur in the simulation that turn into tropical cyclones, or is just that the seeds that you have are in an environment that's more conducive for them to intensify? And I think he concluded it was the latter, although there are a bit more seed to begin with. The dominant role comes from the local conditions. And finally, we also look at future tropical cyclone activity. So on the left, the 4 panels that you have there is the change in track density. Each column is a different tracking algorithm, and the first row is the low resolution, and the bottom is the high resolution. And yeah, the signals are mixed, but there seems to be a fairly consistent decrease in tropical cyclone density over the South Indian Ocean, which is actually has been noted in another study as well. So that seems to be quite a consistent signal in climate model, but for the other basin is quite more uncertain. Yeah, so I'll just for posterity, I'm putting some references there, and then I will just leave you on a short video that was produced here at BSC using a 15-kilometer resolution model. Well, actually, it shows the 3 resolutions that we have used in Primavera: 1 degree ocean, a quarter degree ocean, and then 15-kilometer resolution. And yeah, on this, I think I've used up all my time. Thank you.
Thank you very much, Louis-Philippe. Yes, I think we will maybe won't go until the end of the video so that we have some time for the discussion after our last speaker. So just to remind everyone that you can write down the questions if you have for the first 3 speakers in the questions field. And now the last speaker with us today is John Seddon from Met Office. And John is a software engineer who works on the data management of the Primavera project, a very important component of the project. John, yeah, you can speak now.
Hiya, can you hear me?
Yes.
Perfect. Okay. Sorry, everyone. I'm afraid I had some technical difficulties today, and I'm also in rural England, so I couldn't show my own slides, but Dragana will show them for me. Cool. Go to the next slide, please. Okay, so the biggest sort of challenge in the data management of the project has been the sheer volume of data. So we've had 1.8 petabytes of data generated from 7 different climate models that have been run on high-performance computers, or HPCs, across Europe. Come next slide, please. And so 1.8 petabytes is just it's just a huge number. So can we try and can we try and visualize that by putting it in terms that we might be more familiar with? So 1.8 petabytes is 1.8 times 1000 to the power of 5 bytes, which you can see there. This is equivalent to if we stored this as HD movies on Blu-ray discs, it would take us 16 years of continuous watching to watch this amount of data. I had a look yesterday, and the current MacBook Pros come with a 512 gigabyte hard drive. So Primavera would require over 3,500 laptops to store all of its data. And you can see one of the biggest problems we had in the project was just keeping track of this sheer volume of data. And to put it into context, the coupled model into comparison project 5, which ran in 2013, that produced 1.8 petabytes of data from all the experiments run, all the simulations globally. And so in Primavera, just these 7 models, because of the high resolution, we've produced this amount of data ourselves. So it's been a real challenge for us. Come next slide, please. Okay, so what does running a high resolution climate model involve? What have some of the challenges been? So the Met Office Hadgem 3 HM model has a 25-kilometer resolution between data points at 50 degrees north. And so to get this resolution, we need 768 latitude by 1,024 longitude points around the globe, and then 85 levels up through the atmosphere. And this gives a total of around 66 million points. When we solve this, so every 15 minutes we solve it for every 15 minutes model time, we solve the model on the 66 million data points. On the HPC, we need 2,400 cores to run this model in a reasonable amount of time. And actually, the HPC has very powerful processors. So actually, there's 32 cores on every processor. So actually, we only need 67 nodes, this large chunk of computer, to run this model. And the Hadgem model has been run on the Met Office Cray XE40 HPC in Exeter, where I normally work. And this is currently the 27th most powerful computer in the world. So we really are working with state-of-the-art technology. The other 6 climate models in Primavera have been run on similar HPCs across Europe. So one of the other big challenges in the project was transferring the data from all of these 1.8 petabytes of data from all of these HPCs to a common data analysis platform, where the data is now archived and available for users to access. Can I have the next slide, please? Okay, so data is now in the archive, and it's available for anyone to be able to access through the Earth System Grid Federation, or ESGF. ESGF has been developed as a way of distributing data from the CMIP projects. This URL here, which we'll add onto the Primavera external website shortly, you can access all of our data. And because this is not just the Primavera data, all the CMIP 6 data is also available through this address, then it can be quite hard to find our data. The easiest way to do it is to limit it by going to activity and first of all searching for high-res MIP, limiting it to high-res MIP activity. And then Louis-Philippe has talked about some of the experiments that we ran, so then you can further subset our data by searching on these particular experiments. So high-res SST present and high-res SST future for the atmosphere-only simulations from 1950 to the present day, and then from the present day out to 2050. Then other useful ones, particularly useful ones, are the HIST 1950, the coupled simulation from 1950 to 2014, and then also there's high-res future, which is a coupled simulation that ran out to 2050. Can we have the next slide, please? So here you can see a screenshot from the web page of the ESGF. So here on the left-hand side, I've chosen the high-res MIP activity. And actually some of the data you can see is from the INM model, which is a Russian model, which wasn't part of Primavera. This has also contributed to high-res MIP. So it's not just the Primavera data here, there's some additional data as well. On the left-hand side, you can see how to specify the experiment ID to further subset the data. Then down at the bottom, you can see the variable and CF standard names. The variable names in CMIP, in all the CMIP projects, are very specific to CMIP and may not be that human readable. So if you're unsure what variable you wish to access, then it's definitely worth having a look at the CF standard name, which are human readable. Can we have a look at the next slide, please? So here I've chosen the variable is TAS, which has a standard name of air temperature. So it's much easier to find when you look at the standard name. And again, this is for the HM, which is a 25-kilometer model. And then high-res SST present is the atmosphere-only version of this model. The easiest way to download the data to your own computer is by clicking on Threads catalog. Then you can download the files individually. However, for some of the data sets, then you may find, say, as in this example, there's 65 files, so it'll take a little bit of time to download them by clicking on Threads catalog. The next, and with Threads catalog, sorry, can you go back to the previous slide, please? Yeah, so one advantage of Threads catalog is you don't need to enter a password. It's freely available for everyone to access. What's probably slightly easier to use is by clicking on the wget script. This will download a bash script to your computer, which you can then run with the -H option. If you're on Windows, you can download a bash shell. And if you're working on a Mac or on Linux, then any terminal should run this script quite happily. You may also need to download the wget program, which is a default program that's available for all operating systems. With the wget script option, you will need to register for a free account at CEDA at the address here. This will then give you an OpenID, which when you run the wget script, it'll prompt you for your user ID and password, which you can enter then. And that's freely available. And then the data, the entire data set will download to your computer. As I said earlier, the variable names do require some knowledge of the CMIP6 data request. So I really recommend having a look at the CF standard name, which should make much more sense. So that's all I've got to say. If you do have any problems or have any questions about accessing our data, then please get in touch with PRIMAVERA project through any of the normal methods that you use to contact us. We'll be really happy to help you trying to access the data. Thanks, that's everything I've got.
Thank you very much, John. And now we have some 10-ish minutes, I think, for the discussion. If there are any questions, there should be an icon where you can raise your hand and I can unmute you. And there is also the field for questions. No, I don't see any questions. I have a question it's a similar question, but probably different answers for our first two speakers, for Pierluigi and for Philip. For Pierluigi, what would be your recommendation to a colleague who is starting a similar challenge of preparing such a similar large, very scientific and very novel project of this size? What would be your one wise advice that you learned from Primavera to your friend or your colleague? And then for Philip would be similar when it comes to using Primavera data and your experience with collaborating with scientists in the team, what we call co-production of knowledge. What would be one thing that you would recommend also to a person who is setting now the project, how these things could work better? Can you see?
So for the first part of the question, I would say it's very important to include ensembles in such an exercise. We were not ambitious enough in the inclusion of ensembles. We ended up building on top of the exercise at a later time, but the way the ensembles were run is not homogeneous across the whole community. Perhaps we should have been less ambitious in terms of all the various model formulations and being much more ambitious in terms of ensemble sizes, so that everything could be verified not just by heterogeneous ensemble approach, but also within the internal variability of each model. With regards to the end user engagement, this is obviously a very technical project, breaking ground in many aspects. And I think in many ways, because we were asked to involve the end users, It should have had more time, possibly 5 years instead of 4 years, and perhaps the end users should have been involved in 2 stages, maybe at a very early stage for design, and then told to please wait until we sorted ourselves out and then involve later on in the use of data. But also, in many ways, we should have explained much more that Primavera data are not suitable for direct use. They need to be used with our advice. An example is the study we saw on rivers. One of the big caveats of Primavera is that the models are not tuned, because we want to understand resolution. We don't want to produce the best possible beautiful result without understanding what is the cause of that. Is it the resolution? Is it all the tuning? So in many ways, such intercomparisons may confuse people, because in some aspects or in some regions, the models will perform better, where the resolution really has an effect. But in other regions, possibly away from orography, away from coupling regions, the models could perform much worse. And that's again because the purpose here was understanding, not the most beautiful end result. And it's very difficult to explain this. It takes time.
Thank you, Pierluigi. I can't agree more. And Philip, would you like to comment on this also? Okay. I think you have the sound now.
Okay. Yes. Hi. Yeah, maybe what I can say from our little using exercise, probably 2 things. One draws on what Pierluigi has said, that it is a very technical project. It is probably not best suited for a co-production exercise. Many different users that would have been included would maybe have different focus points, but most of them would probably not be possible to accommodate. And the focus here is on scientific questions, and then also all these computing powers and that are behind it probably don't allow accommodating all the user wishes or all user inputs. But I think it would have probably been good to include the users at an earlier point, as Pierluigi said, and then maybe much later we were addressed or we were approached to be part of this exercise at a rather late stage, I would say. Everything was already defined. And from a very practical point of view, if you expect users to contribute a lot, it is also better to include them early, and also to include some funding for them, because there was no funding for users, as far as I know. At least we didn't receive any. But I think it is really also maybe not the best. It depends very much on I think on the general research question of a project, if it is at all at that if a co-production framework fits into it at all. Maybe this project is not the best project for a co-production framework in general.
Thank you, Philip. But I think we still went quite far with this collaboration. So we have one raised hand and one question from the audience. I will first give unmute Mr. Kimoto, if you would like to ask your question. Okay. Yes, Mr. Kimoto, would you like to ask a question?
Yes. Can you hear me?
Yes.
Okay. So this may not be a straightforward question, but more of a comment. But I'm from Japan, and I'm going to sleep. But before I go to bed, I would like to congratulate the great achievement of the Primavera project as an external advisory, one of the members of the external advisory board. and many of the positive impacts of the resolution is striking. And I really would like to know, I mean, I really would like to hope that the Primavera readers work to produce synthesizing report on their achievements, and not only the pros of the resolution, but also the aspect of the climate that has not been very much improved by the resolution. All this overall picture would be very beneficial to the community to make further advancement in this field. So I really would like to see a big kind of a table-like thing in which you list various aspects of the climate and impact of the resolution, at not so much impact of the resolution, and issues about the tuning, resolution, and data handling matters, and so on and so forth. And of course, I've heard that Pierluigi and other leaders of the Primavera are preparing for a BAM's paper, what they call, synthesizing all the results. But of course, you have many papers describing the individual aspects of the impacts and on various climate phenomena. But probably something that can give the community pros and cons of the resolution impact as a table or something that gives you as a glance would be very beneficial. Specifically, Pierluigi, can you give me a few examples of I had many interesting impacts of the impressive impacts of the resolution, but can you give me a few examples that you may still have way to go, not just the resolution, but also physics tuning or something like that, about climatological phenomenon like blocking or storm tracks and things like that?
Can you hear me?
Yes.
Oh, okay, great. I thought I was muted. So thank you for the comments, and I think your suggestion is very valuable to the paper, to really be fully honest. It makes the paper even harder, but I think what you suggest is really important, to really disclose where there is value and where there isn't. In terms of providing negative examples, I can tell you we have a paper that is about to be submitted to Journal of Climate assessing all the rivers in the world. And it is certainly true, and here we are trying to understand whether the rivers are better simulated with the atmosphere of the high resolution models or worse simulated. It is certainly true the near orography, and this we knew from regional models, but now it's a comprehensive global study. Wherever we have mountains, we tend to win on the high resolution, but actually over much very, very flat terrain. And an example is the whole Nile catchment, which is a huge catchment. In that place, the high resolution is doing worse than the low resolution. And what we need to understand there is whether it is the circulation that is for some reason wrong in the high resolution, or if it is really that the low resolution model was tuned and in many ways is now doing quite well because everywhere is quite flat, and then everything is tuned to that situation, while the high resolution wasn't tuned, and then it is penalized over flat terrain. There is a lot of research to be done there, and we are trying in the paper to detangle this. An example you asked about blocking, we certainly see there is virtually no improvement in using the high resolution for blocking. And this could be because the range of resolution that we addressed in Primavera is insufficient, or it could be because really that is a phenomenon that depends on other things, and potentially the quality of the orographic drag. We're never going to fully resolve orographic influence on atmospheric flow, even if we were to go down to a kilometer. Maybe even then we wouldn't do it properly. But certainly that is an example of something that gave us some hope in the past, but in this case, from these studies that we conducted, we don't see it. The other aspect is the intensity of hurricanes. There is one model in the whole ensemble that has a really, really good relationship between pressure and wind in hurricanes at 20 kilometers. And I think that model is actually wrong. That at that scale, it shouldn't do it. From the diamond simulations, between 3 and 5 kilometers, we're starting to do that, but not quite. So if we really want to understand the full impact of hurricanes in the climate system, even such models are not enough. So we will ever get to it, even when we have the 1 kilometer models, but then we might not be able to ever run such models in large ensemble mode and long enough to really understand the climate impact of hurricanes. So maybe we need to come up with much cleverer methods. Possibly, if that is what we want to understand, just the role of hurricanes in the climate system, we could use mesh refinement, like Christiana Jablonowski has done in the past. Maybe there are other specialized ways to answer some of the questions. So there are examples of situations in which the resolution hasn't done, it hasn't been the magic bullet. But I think of all the things I've seen, the fact that for the larger area changes in precipitation and some other properties of circulation like storm tracks and all that, both tropical and extratropical, the models agree so strongly with each other. That is actually giving me much hope that if we focus on circulation and we focus on dynamics, there could be quite strong understanding of what convergence zones are, areas of coupling, the interaction of eddies with jet. Those things we might actually make big progress on. And then in the future, maybe I think we could work a lot more with the Cordex community and exercise the best of the two worlds, or the best of our circulation and the best of the explicit convection they can achieve with these very advanced regional models they have nowadays, and perhaps understands much better the role of convection with the proper sample size. That's the problem, that if we go to those scales, we don't have a proper sample size, and we're left wondering what it all means.
Okay, thank you very much. I'm not, trying to dig the weak points of the Primavera, but since you have so many of positive and impressive results all the way, that makes your issues as outstanding as the community to tackle or challenge in the next stage. So that kind of information is very valuable. That's why I'm asking this question. Another small point is that there was you didn't mention today, but there was a talk or some statement from somebody in your member that there was a teleconnective improvement in European regional scale climate phenomenon coming all the way from the east coast of the United States or something, and then the physical process improving the storms, and then teleconnecting to bring the better simulation in the climate in Europe, something like that. That sort of thing, not the in situ improvement due to the increased resolution, but through the atmospheric processes, the systematic improvement of resolution affect the remote region. That sort of knowledge is very valuable, so that not just this becomes better, this becomes worse, but also the investigation into the processes that are occurring in the higher resolution model would also be very valuable. Sorry about the long comment, but
No,
congratulations.
That makes it justifiable to use global models. Otherwise, we might as well just use regional.
That's right. Yeah, that's it. Yeah.
Yeah.
Okay.
Thank
you very much.
Thank you. And the next question from Ms. Jablanovsky, I think follows up on this discussion. She asked about the future of the Primavera team. And is there a chance for a follow-on project to be funded, and what should its focus be? I think Luigi or also John or Louis Philippe, if they want to comment on this.
I can comment a bit. So we have submitted 2 projects to the European Commission under the Horizon 2020 program. One is very much the same team as Primavera and will focus on exploiting the high resolution in the ocean. So we have developed these ocean models at 1/12 degree, and we've seen much happening in the ocean in terms of circulation and also in terms of coupling with the atmosphere. The idea is to then exploit these models over a range of applications, basically from bursts of seasonal simulations all the way to very long, really very long, 250, 300-year long simulations, coupled with the atmosphere, possibly in our case at the same resolution, for other groups possibly at a bit less resolution, but with the idea of understanding these eddy mean flow interactions basically in both systems. So this is really about the eddying in the ocean. We are certainly eddy permitting. I wouldn't say we are eddy resolving, but we are strongly eddy permitting in that regime. And also with a strong focus on the ability to initialize such models. So there are lots and lots of technical aspects about initialization, spin up, accelerated spin up. But really it is all about exploiting these high resolution oceans and the predictability signal therein, and this whole paradox of signal to noise in the atmosphere and all that. The other project, which is a much smaller group, is led by Max Planck and aims to further develop atmospheric models in the sub 10 kilometer range, with the aim of producing a climate simulation at about 3 kilometers with at least 2 European GCMs by the end of the project, and so in about 6.5 years' time. And that has Reading as a participant, but sort of a minor participant, because at the moment we don't have a model that would be performing from the point of view of numerical efficiency as well as these newer models. So what they intend to use there are the newest versions of the Max Planck ICON and the ECNWF IFS, which numerically perform very well. Our model is in a transition state, and we might do the simulations for ourselves, but not as part of funded research. But we will do analysis of hurricanes, which is a very strong interest of ours, and the interaction between hurricanes and the large-scale environment in that project. So there are two streams of new developments and simulations. One is really a classic GCM coupled GCM exercise, which I would say is a true follow-on to Primavera, and it's called Summer, and so which means summer in Swedish. So after spring you have summer. And the other one is Next Gems, and is a Max Planck-led project, which is basically inheriting the spirit of the frontier simulations that we had in Primavera. So,
Christian, is there anything else you would like? Is there any reaction to this, or there's something else you would like to ask?
Yeah, thank you, Pierluigi. Also, congratulations to the Primavera team. I think you have great accomplishments, and this was really showcased today. And also, which I couldn't quite join, but during your Primavera General Assembly. I'm very happy to hear that you have 2 proposals, at least in review, which of course are probably not decided yet, but I really think there's so many lessons that we learned here, and so many good conclusions. And I'm also very happy to hear that you want to highlight the things that didn't work or didn't improve with resolution, that this should really lead into the future. So I'm very satisfied with the answer, so I don't have a follow-up question. And again, congratulations to the team.
thank you to both. You're both very kind. Thank you very much. I'll transmit the congratulations to the rest of Primavera.
Thank you. Is there any reaction from Louis Philippe or John to the last question?
No, nothing from me. Thank you.
Yeah, I'm good, thank you.
And I think our last question was from Philip to John. Maybe Philip, you want to ask it directly.
I was just wondering, John, you showed that the data can be downloaded from the ESGF portal. And as far as I remember, there's no way of restricting the download to a specific domain there. But I was wondering if there will be any possibility for the GCM data of Primavera to restrict the download domain-wise, because if you download the full data set, it makes quite a difference if you have to take the globe in this resolution, or if you just take the basin that you're interested in.
Yeah, unfortunately, ESGF will only allow us to download the entire domain, I'm afraid. Yeah, there's no way to subset it. If you do want to subset it, it's almost worth contacting CEDA and trying to get an account at Jasmine, and then it's easier to work. You can actually work out the archive, and there's various, I think there's some ASUS proposals, so you can get time at Jasmine if that helps you. But yeah, if you need any help getting access to Jasmine, then please get in touch with us, and we're happy to help you. That would save you having to download the entire domain.
Okay, thank you.
Okay, is there anything else someone would like to say for the end from the panelists or from the audience? Yeah, no, then I think we can close here. Thank you very much. Very interesting presentations, and thank you also for the participants. We lasted the webinar lasted a bit longer than we planned. Sorry for that, but I think it was worth staying 15 minutes longer. And just to remind you that we will have the presentations also broadcasted at our user interface platform in a few days. Have a nice afternoon, everyone. Goodbye.